Hi everyone, I'm Jack. Today I'm presenting our work, Jailbreak Distillation, Renewable Safety Benchmarking. Our problem is LLM safety benchmarking, which has become increasingly critical because we need to uncover model safety vulnerabilities and compare the safety across models. And in fact, measuring AI risks is an important pillar in the NIST AI risk management framework. Existing safety benchmarking paradigms are actually not super robust. This is because for static benchmarks, for example, human-curated attack prompts, such as the do anything now prompts, they tend to saturate over time, and they can get contaminated by new models because they're static, and it is costly to rebuild these benchmarks. On the other hand, we have dynamic evaluation, for example, automatic red teaming algorithms, such as GCG and TAP jailbreak attacks. These attack algorithms are very effective. However, they spend a different amount of compute on different models, rendering the results somewhat incomparable. Moreover, attack results are sensitive to randomization or small parameter change. Then you have reproducibility issues. Now the question is, how can we find the best of both worlds between the static and dynamic safety evaluation? We propose jailbreak distillation to achieve this. Static prompts are used during evaluation, making it comparable and reproducible. On the other hand, it is easy to regenerate new benchmarks with new models and attacks. This alleviates saturation and contamination concerns. Jailbreak distillation builds safety benchmarks in two steps. First, we transform the seed goals that are vanilla harmful requests into a candidate prompt pool. Next, we select a subset of effective prompts from the candidate pool as the output benchmark. First, the seed goals looks like vanilla harmful queries, such as how to build a bomb. And then we attack the development models using off-the-shelf attacks as transformation functions to construct the pool. We use off-the-shelf jailbreak attack algorithms as transformation functions, and we run attack algorithm attack against a group of development models and collect attack prompts. For example, the more sophisticated strings that can lead to unsafe behaviors. For the second step, we select prompts using success on development models as proxy for broad effectiveness. So the intuition is, if prompt A broke 3 development models, but prompt B only broke 1 development model, then A is likely, in general, a stronger prompt than B. Building upon this intuition, we propose several prompt selection algorithms that select a subset of the pool as a final benchmark. And we use the attack on the seen set of development models as a proxy for effectiveness. We propose different prompt selection algorithms, including rank by success, which greedily select prompts that break the most amount of dev models, best per go, which select the best prompt per seed goal in a balanced behavior, and finally the combined selection algorithm, which do BPG first to select a single prompt for each goal, and then we do RBS. Now we present a unified algorithm for jailbreak distillation, which we can see that it materializes the two-step approaches we discussed. The question next is, how do we evaluate the safety benchmarks we have built? We evaluate a benchmark B using a group of held-out evaluation models. These evaluation models are not seen during benchmark construction, and we propose several desiderata for good safety benchmarks. First, we have effectiveness, where high effectiveness indicates that benchmark B achieve high average attack success rates on the group of evaluation models. Second, we have separability, which measures the ASR confidence intervals of pairs of evaluation models. And if the attack success rates confidence intervals do not overlap, then we say two models are separable. And for the separability metric, we simply measure the proportion of pairs that can be separate. Finally, we measure diversity, which indicates that the B covers and is effective on a wide range of seed goals. We use HarmBench standards as our seed goal sets. And for development models that are small-scale open source models, we use these because they are easy to obtain and deploy. Moreover, because these are open source, we can use white box attacks on them and then transfer to models that are only available black box via API. So this will make our approach more general. For transformation functions, we use 4 single-turn attacks: tap, pap, adversarial reasoning, and autodone turbo, and 4 multi-turn attacks, including CCA, Red Queen, Speakeasy, and Actor attack. For evaluation models, we use 13 diverse models, which includes larger models, newer models, reasoning models, and specialized models, all of them unseen during benchmark construction process. For the evaluation judge, we use the add prefix judge, where we also develop a multi-turn variant with high human agreement. Finally, our results show that jailbreak distillation is effective on a broad range of models. Here we see that the average ASR on the development model is 84%, and on the right, we generalize very well to evaluation models unseen during benchmark construction. For example, we break Llama 70 billion with very high ASR and almost as same as the Llama 3.18 billion. Moreover, we also jailbreak O1 over 60% of the time. Jailbreak distillation also outperformed both static and dynamic approaches that are prior works. Compared to the best baseline, we have 81.8 effectiveness, where the PAT algorithm that achieved the best effectiveness across the baselines only achieved less than 70%. We also find that prompt selection algorithms are crucial for effectiveness. Here, we show that the random selection baseline algorithm only have 53% effectiveness, and our rank by success algorithm have more than 80% effectiveness. So this shows that instead of generating more transferable prompts, which are prior works focus, we can simply select transferable prompts that works extremely well across different models. So basically, we can over-generate the filter instead of having to generate one prompt that is super effective off the shelf. Here, we find that if we add more models or more attacks, then we get a stronger benchmark. This is crucial for making the benchmark renewable, because then we can just keep adding the newest model or the newest developed jailbreak attack algorithm to our framework, and then run the algorithm again to get a new version of the updated benchmark. To conclude, we propose jailbreak distillation, a benchmark construction framework that distills jailbreak attacks into high quality and easily updatable safety benchmark. By doing so, we achieve the best of both worlds between static and dynamic safety evaluation, tackling saturation, comparability, and reproducibility challenges. We link a QR code to our paper, and thank you so much for watching.